In this lesson, we're going to look at energy and motion. The first aim is explain how to calculate work done and power, then explain how to calculate kinetic energy and gravitational potential energy, and finally, can you calculate velocity using kinetic energy and apply the law of conservation of energy. In other words, this is quite a mathematical lesson, but it's interesting maths because it's maths that informs you about the world we live in. As a physics teacher in the school I work in tells me, if he could explain physics in words he would, but it's much easier in maths. So we've already looked at how motion can be described in terms of forces, looking at drag, thrust and stuff like that, but we haven't looked at the idea of how motion can also be described in terms of energy. As you can see, these balls are moving, and we could definitely describe the motion of these spheres in terms of energy, and hopefully you'll be able to do that by the end of the lesson. But moving an object requires effort, and energy is needed to make that effort. And we get this energy in the form of food, chemical potential energy, electricity, electrical potential energy, and obviously fuel, another chemical potential energy. When someone exerts energy to basically move an object, we say they are doing work. Work is another way of saying we are transferring energy. So in this example, the food which this boy's eaten is a source of chemical potential energy, and that's transferred to kinetic energy in the moving bin when he moves the bin. So some of the work carried out by this person is due to energy being transferred to useful forms, but also as they're moving it, there's going to be friction here, and so there'll be heat produced, sound produced, and these aren't useful. All the boy wants to do is move this bin, and so some of the energy is transferred as wasteful forms of energy. But they both come under the umbrella of work, the energy transferred to move this bin. So work is done when we exert energy to move an object. Therefore, work done is a measure of energy transfer, so it's measured in joules. And we are applying a force to an object and moving it a certain distance. So we work out work done by multiplying force in newtons by distance in meters. For example, let's say I'm playing tug of war with this dog here, and I exert a force of 600 newtons to pull the dog towards me by a distance of 2 meters. Work done would simply be the force I applied to move the dog, 600 newtons, and the distance over which that force was applied, 2 meters, multiplied together to give us the work done value of 1200 joules, 1200 joules. So this is a really easy formula, and you'll find it in the front of your exam papers. Remember, work done is a word for energy transfer, and therefore it's measured in joules. Now, we've already looked at power in terms of electrical power, which we multiply current and potential difference together. But power, more specifically, well, it's a measure of how much energy a machine transfers in a specific amount of time. So a powerful machine is one which transfers a lot of energy in a short amount of time. This is why power in watts can be worked out by doing this. Work done, energy transferred over time. So for example, if a weightlifter transfers 2 kilojoules to lift a weight in 3 seconds, so from here to here, and that takes 3 seconds, calculate their power. Well, the work done has to be in joules, not kilojoules, so it would be 2000 joules. 2 kilojoules is 2000 joules, 1 kilojoule is 1000 joules. And the time taken is 3 seconds. So the power would be 2000 divided by 3, and that gives you a reading of 666.7 watts rounded up. But remember, because a watt is essentially joules over time, joules per second, we can also say 1 watt is equivalent to joules per second. So the unit for power is either joules per second or watts, energy over time. And that's how you explain how to calculate work done and power. So now we're going to look at 2 very important forms of energy, especially when discussing energy and motion. These are gravitational potential energy, which you can abbreviate to GPE, and kinetic energy, which you can abbreviate in exams to KE. All energies, such as GPE and KE, are measured in joules. So basically, gravitational potential energy is the energy an object stores at a height. So you can see this mug is resting on a table, and it is at a height and therefore has stored some gravitational potential energy. Now when it falls, it gets less and less. The value of GPE gets less until it gets to the floor where it has no GPE. So the point is, the higher an object is, the more GPE it has. So here it has the maximum amount of GPE in this example. So GPE can be calculated by multiplying weight by height. But remember, we're making a link to another equation. Weight is calculated by mass of an object by the gravitational field strength of our planet, which is always 10 newtons per kilogram. So just remember, G, the gravitational field strength on Earth, is always 10. So mass times 10 will give you weight, and then you multiply it by height. So in this example, we've got our mug, which is 500 grams. That's its mass. But remember, mass has to be in kilograms, so 500 grams is 0.5 kilograms. We know G is 10. And the height our mug falls is going to be 60 centimeters. So GPE would be 0.5 kilograms times 10 newtons per kilogram for the gravitational field strength times the height, 0.6 meters. Notice how I had it in centimeters here, but in a formula it has to be in meters for this to make sense, and you get 3 joules of gravitational potential energy. So just remember that weight times height is going to give you GPE, and remember you can calculate weight by multiplying mass and the gravitational field strength, which is always 10. Now let's look at arguably the most complex formula in GCSE physics. That's the one for kinetic energy. Now, kinetic energy is the energy in a moving object. So how fast the object is moving, velocity, and how large that object is, mass, both affect kinetic energy. So if you're moving very quickly, you're going to have a lot of kinetic energy. But if you are a larger object and you're moving as quickly, you're going to have even more kinetic energy because you have more atoms that are moving that quickly, and each atom is a store of kinetic energy. Kinetic energy has the formula half mv squared, where m is mass and v is velocity. Just like momentum, which also takes in velocity and mass into account, so does kinetic energy. But how would you write that in a calculator? Well, if you ever had to calculate kinetic energy, you would literally type this into your calculator. 0.5 for half, multiplied by the mass, which will be given in the question, times velocity, which will also be given in the question, and that accounts for velocity squared, v times v. So let's use this as an example. This is my greyhound. I've let her loose in a tennis court. It's the only time she gets a chance to run as quickly as she can. My greyhound weighs 20 kilograms and runs at a maximum velocity of 20 meters per second. That's very fast for a dog. Could you calculate her kinetic energy at this maximum velocity? So assuming she's running at a constant 20 meters per second and weighs this much, how much kinetic energy does she hold or have at maximum speed? Well, it's simply a matter of plugging everything into this equation. You do 0.5, which is the given in the equation, that doesn't change, multiplied by mass, which is 20 kilograms, multiplied by velocity, which is 20 meters per second, by velocity again, 20 meters per second, which will give you 4,000 joules of kinetic energy. May look complex, but actually it's quite easy. You're just plugging in the numbers where you see them into this formula. But here's where it gets a little bit more complicated. We're going to make a link to the car safety video here, where kinetic energy equals half mv squared, which also equals force times distance, which is another way of expressing work done. What does this have to do with cars? Well, firstly, understand this. There are 2 factors involved in kinetic energy, mass and velocity. If you double the mass of an object, you will double its kinetic energy. However, because v is squared, if you double the velocity of an object, you will quadruple the kinetic energy it has. In other words, increasing your velocity is much more dangerous than increasing your mass in terms of a collision. Now, when we apply the brakes on a car, we are doing work. We are applying a force over a certain distance. And whatever this value adds up to, or when you multiply them together, equals, it has to equal the kinetic energy. That's what equations are. It means everything's balanced on every side of the equation. But here's the thing. You can only push the brakes down so hard, so far, so there's a maximum limit to how much force you can apply. But kinetic energy can be way beyond this level. So what that means is the distance traveled will increase. The brakes will only take you so far. So if you've got a lot of kinetic energy, you will travel a further distance. To put it another way, imagine you have 2 cars of the same mass. One is traveling at 30 miles per hour, the other one at 50 miles per hour. And this bar represents how much kinetic energy the car has at that speed, velocity. Now let's say you're trying to brake and you apply the brakes. The force applied to basically put down the brakes will cause energy transfer. Obviously, when you apply the brakes to the wheels, you create friction. Friction creates heat, so you're going to get energy transfer. But only so much. As I said, there's a maximum limit to how hard you can push the brakes. So let's say 50 kilojoules of that kinetic energy in the moving car can be transferred to heat as the car brakes. But obviously at 50 miles per hour you have way more kinetic energy. So that means a lot more energy transfer has to occur between the wheels and the road. So energy is transferred due to friction or tire friction against the road before the car can stop. My point is, at higher velocities, you'll have more kinetic energy, so you'll travel a greater distance because braking only takes you so far. It only causes a fixed amount of energy transfer. So to make sure the equation's balanced on both sides, you travel a greater distance. This is what I mean when I say that equations in physics do tell you something useful about the world around you. And that's how you explain how to calculate kinetic energy and gravitational potential energy. Now we're going to look at the most complicated rearranging of an equation in GCSE physics to date, and that is calculating velocity of a falling object. Now don't get confused here, I know you can calculate velocity using distance over time, but you can also calculate it using the kinetic energy equation and rearranging it. That's what makes it more complex, but it's actually not that difficult once you sort of filter out the noise and understand the few basic steps you need to take. So hopefully this diagram isn't too confusing. Basically, this is the setup. We have a monkey in a tree and our monkey weighs, let's say, 12 kilograms. And what I want to find out is, as it falls, what is going to be its maximum velocity just before it impacts with the ground? Now, to work this out, we need to use three different equations. That's why this is fairly complex. The first equation is our GPE equation, weight times height, or mass times gravitational field strength times height. The second one is something called GPE lost equals KE gained. I'll talk about that in a second. And then finally, kinetic energy equals half mv squared. Don't let this scare you, it's really not that difficult. So step one is work out the GPE the monkey has. So before it falls, how much GPE does it have? And to do that, you just need the height, how high up it is in meters, and you need the mass times the gravitational field strength. So we have the mass, you'll have that in the question, and you multiply that by 10, then multiply it by 10 meters, because that's how high up it is, and that will give you 1200 joules. So that's easy, that's step one. So now we know how much gravitational potential energy it has up here, but now we need to work out how much kinetic energy it has down here. This is a lot easier than it sounds if you use this equation, GPE lost equals KE gained. In other words, at this point, its GPE is maximum, but it's not moving, so its kinetic energy is zero. And as it falls down, that GPE we transfer to kinetic energy in the monkey as it descends, until it gets to the bottom where its GPE will be zero and all of that GPE will have been transferred to kinetic energy. In other words, the GPE lost is the same as the kinetic energy gained, so it will have 12,000 joules of kinetic energy just before it hits the ground, because 12,000 joules of that GPE has been completely transferred to kinetic energy. In reality, this doesn't actually happen, but we'll discuss that just in a bit. But for now, in these sorts of questions, you can assume it's a perfect transfer. So now the tricky bit. Now we have to use the KE formula, but we have to rearrange it. The first thing you do is not touch the equation, you just substitute the known figures into the equation. So we now know the kinetic energy is 12,000 joules. We don't have to calculate it because we've used this formula to work it out. So all that GPE has become KE. We know 0.5 is the half, that's always the same. We know the mass is 12 kilograms. What we don't know and what we need to calculate is velocity. But to do that, we have to basically unpackage this equation, reverse what's been done to it. So you can see the first thing that happens is this side of the equation has been multiplied by 0.5. To get rid of this, we have to basically divide this side by 0.5. But it's an equation, so we have to divide both sides by 0.5. So the effect of dividing this side by 0.5 is we get rid of it on this side, and we must divide this side by 0.5 because, as I said, it's an equation. What happens on this side must happen on this side. When you divide a figure by half, it's the same as multiplying it by 2, so you don't actually need a calculator, you just double this figure. So that tells us that 2,400 joules equals 12 kilograms times velocity squared. Now, this side has been multiplied by 12 kilograms, so to get rid of it, we must divide by 12 kilograms on both sides. The effect of doing that is the 12 kilograms no longer appears on this side, and we must divide this side by 12 kilograms. And if you do that, you'll find that 200 equals velocity squared. But we need to find out velocity. So what's been done on this side? Well, it's been squared. How do we undo a square? Well, we have to square root on both sides. By square rooting on this side, we get rid of the square, and by square rooting on this side, we get the answer. So the square root of 200 is 14.14 meters per second. Now, this may seem very lengthy and it may seem like this is too much to remember for an exam, but just remember it can be reduced to 3 simple steps when you're rearranging this. First, divide the kinetic energy by 0.5, then divide that answer by the mass, then square root that answer, and you'll get your result. Divide by 0.5, divide by mass, square root. That's it. But I think it's absolutely essential that you have a go at this because you're just not going to remember it unless you work through it yourself. So imagine this setup. You have a roller coaster and you have your cart at the top. The cart weighs 500 kilograms. And what I want to know is, what's the velocity of the cart by the time it reaches the lowest point of the roller coaster? You're given everything you need to know. You know the height of the drop. You know the mass of the cart. Just remember the following steps. First, you work out GPE. Then you work out kinetic energy using the formula kinetic energy gained equals GPE lost. And then you have to rearrange the kinetic energy equation using these 3 simple steps. Have a go now. Okay, so the first thing you have to do is work out the gravitational potential energy. And you can do that by multiplying mass by gravitational field strength, always 10, by the height, 20 meters, which you can see here. Doing that will give you 100,000 joules. Next, it's the simple equation GPE lost equals kinetic energy gained. So we've lost 100,000 joules, so it must have been transferred to kinetic energy by the time it gets to the bottom, 100,000 joules here. So here our cart has 100,000 joules of GPE, and by the time it gets to the bottom, it's all been transferred to kinetic energy. Now we're just going to take my shortcut to rearrange the kinetic energy equation. Divide by half, divide by mass, then square root your answer. So we divide kinetic energy, 100,000 joules, by 0.5. That's the first step. That will give you 200,000. Now we divide by mass, the mass of the carriage. 200,000 divided by 500 gives you 400. And finally, we square root 400 to get our answer. So the velocity of the moving carriage will be 20 meters per second by the time it gets to the bottom. Practice as many of these as you can by looking at past exam papers. Now let's try some application. You may remember conservation of mass, you may remember that momentum is conserved, and so is energy. But we need to apply this knowledge of the law of conservation of energy, and this can come up in a number of ways in exams. Here's probably one of the most challenging ways in which it comes up. But like most things, it's easy once you know it. Firstly, look at this graph. We've got kinetic energy on the y-axis and time on the x-axis. And what we can see is some object is gaining kinetic energy, then the kinetic energy in the object is decreasing, then increasing, then decreasing, and so on and so on. But what's also important is throughout, the maximum kinetic energy is going down as well. You may be asked to explain a graph like this. Well, you could relate this motion to something like a swing or a pendulum, but I'm going to use a bouncy ball for this. So firstly, let's explain the rise and fall in kinetic energy. Well, let's say I'm holding this ball in my hand at a fixed height. So at this point, its GPE is max, and let's say its GPE is 50 joules. As I let it drop, the GPE decreases 40 joules, 30 joules, 20 joules, 10 joules, 0 joules. But this whole time, the kinetic energy is increasing because energy is conserved. It's not lost. If it seems like it's decreasing, what's happening? It's being transferred to another form. So the GPE in the ball is being transferred to kinetic energy, and it gains more kinetic energy as it drops and accelerates. So at the bottom, GPE is 0, whereas KE is maximum. All that GPE is being transferred to kinetic energy. And when it bounces up, the opposite happens. So GPE starts to increase and kinetic energy starts to decrease. So as the ball bounces up, it starts to slow down until it reaches its maximum height, where basically all the kinetic energy in the ball has been transferred back into GPE. So you can see from 50 to 40 to 30 to 20 to 0 KE, but from a GPE perspective, 0 to 10 to 20 to 30 to 40 to 50, back to max. So that explains the rise and the fall, but it doesn't explain why the maximum KE is going down. And that's because, truthfully, there are more energy transfers occurring, and you know this. When the ball drops, it's colliding with air particles, and those air particles are a source of friction, so you're going to get heat transfer out from this system. So basically, some of that kinetic energy, or GPE, will be transferred to heat energy, to the surroundings. When the ball hits the bottom, there is more friction, therefore we get more energy transfer as heat, and also we hear a sound, a thud, so we get heat and sound. This energy lost as heat and sound is chipping away at this reserve of energy, so it eventually declines. So firstly, as the ball falls, GPE is transferred to KE. That's this point on the graph. So just before the ball hits the ground, we're at KE max. Then as the ball bounces upwards, that kinetic energy is transferred back to GPE. So that's what's happening as it bounces back up. So that would be this point on the graph. So KE is now 0 and GPE is max. I would definitely state that because that will get you a mark. So when GPE is max, KE is 0, and when KE is max, GPE is 0. So we've explained the up and down, now we just need to explain the overall decline in KE max. So as this process continues, some energy is transferred to the surroundings as heat and sound due to friction and air resistance, which to be fair is another form of friction. So we can see that over time, that ball will start to bounce less high until it stops bouncing altogether because all of that energy has been transferred to the surroundings as heat and sound. This is why KE max decreases. In fact, if you have to describe any reason in terms of energy why a moving object stops, it's because of transfer to the environment as heat and probably sound too. Think about it, when you apply brakes to a car, you're stopping because that kinetic energy is being transferred to the surroundings as heat due to the friction between the brakes and the tyres. If a skier suddenly comes to a stop downhill, it's because the kinetic energy that they have while they're moving is being transferred to heat to the environment as basically the skis create friction against the snow. And that is how we calculate velocity using kinetic energy and apply the law of conservation of energy.